Cool. Yeah, so I'd like to thank the organizers for setting everything up and for the opportunity to speak. Yeah, so I'm going to be talking about minimal surfaces and quasi-Fuchsian manifolds. And so the first part of my talk is just going to be a brief overview of quasi-Fuchsian manifolds and how they're studied with minimal surfaces. And then I'm going to move to recent work that I've done on that subject with Xeno1. All right, so quasi-Fuchsian manifolds. So what those are just hyperbolic structures on a surface of genus bigger than 1 times r that are well behaved at infinity. Which I'll say a little bit more about that in a second, but yeah, and so for quasi-Fuchsian manifolds, it's kind of maybe the simplest topological situation in kind of three-dimensional hyperbolic geometry, but where you get complicated geometry. So there are kind of all these different ways of putting a hyperbolic metric on a surface times r. Even though, I mean, topologically it's quite simple, like compared to, I don't know, like closed hyperbolic three manifold, which is kind of like impossible to visualize. But if you just have like a surface times r, you kind of know exactly what's happening with the topology, but what's going on with the geometry is kind of yeah, much more intricate. Yeah, and I guess, I mean, one place where, I mean, quasi-Fuchsian manifolds are really important is like Thurston's hyperbolization theorem for closed for manifolds that, I mean, fiber over the circle. And so kind of how that's proved is you have this hyperbolic structure that you want to construct, and so you sort of pass to you have a manifold, three manifold that fibers over the circle. You pass to the cover, you pass to the z cover that kind of corresponds to like unwinding it around kind of the base S1. And then how you get the hyperbolic structure is by kind of approximating by quasi-Fuchsian manifolds and like passing to a limit. Yeah, and so I guess they're important for that theorem, for example. And I mean, they come up a lot in hyperbolic geometry just because I mean, yeah, if you have a surface in a hyperbolic three manifold, and if you just I mean incompressible surface in like a closed hyperbolic three manifold, say, if you pass the cover for that surface, then it'll often be a quasi-Fuchsian manifold. And so yeah, so these come up a lot. Right, and so yeah, so maybe the first kind of the model case, like the trivial case for quasi-Fuchsian manifolds is if you just take a hyperbolic structure on a surface of genus G, then that's kind of the same as specify the hyperbolic structure is the same as just specifying kind of the holonomy. So just kind of this map from this representation of the Pt1 of the surface in PSO2R. And so if you just include that in PSO2C, which is the isometry of three-dimensional hyperbolic space, then what you're going to get is this, yeah, you're going to get this hyperbolic structure on a surface times R, or there'll be a quasi-Fuchsian, or I mean, there'll be a totally geodetic surface in the middle that kind of corresponds to the hyperbolic structure that you started with, and then it'll be kind of flared out. But in general, like in this picture I drew, if you have a quasi-Fuchsian manifolds, and what I mean by saying that it's nice at infinity is that it's flared out in this predictable way where you can basically write down the metric explicitly. But in the middle, in kind of this convex core region here, that's where kind of like all the action is happening. And so there's this sort of right, there's this like minimal convex set in the middle called the convex core. It's kind of just this canonical convex set in the middle, where yeah, you kind of don't really know what's going on, but near the ends you kind of have this yeah, exact idea of what's happening if you're quasi-Fuchsian. And yeah, and so I should say is that, I mean, as I already kind of mentioned, I mean, you can have lots of hyperbolic metrics on the surface times R that are not quasi-Fuchsian, that kind of do not flare out infinity in this nice way. And so one example that I was kind of saying was if you I mean, if you have a closed hyperbolic three manifold that fibers over the circle, and if you take the z cover of that corresponding to unwinding the base, then you get this hyperbolic structure on a surface times r, but it'll be kind of have uniformly bounded width as you go up, so it will not flare out like what you have if you're quasi-Fuchsian. And so and it turns out there are lots of other examples. So probably like these like degenerate examples are more common than quasi-Fuchsian manifolds. But right. So okay. So yeah, just to kind of say a little bit more about what kind of we get from what being nice in infinity means. Is if you take the limit set of the quasi-Fuchsian manifolds, what I mean by that is I mean, so we have this hyperbolic metric on the surface times r, and if we just pass to the universal cover, right? So we're can write our quasi-Fuchsian manifold as the quotient of H3 by this action of pi1 of a surface. Okay, and so if we just take there's some close subset of the boundary at infinity that's just all the accumulation points of the action of pi1 of the surface on the universal cover, right? And so if we're quasi-Fuchsian, then this limit set, it ends up being a Jordan curve. Okay, so it ends up being nice. Like it could be something bad, like it could be like the whole S2 at infinity, or something else that's bad. But if we're quasi-Fuchsian, then because we have these kind of like nice control on the ends, we know we kind of know the boundary infinity has to be this Jordan curve. And so, for example, if we're in the Fuchsian case, right, the kind of the trivial case I just mentioned, it's just going to be like the limit set's just going to be a round circle. But in general, it's going to be this Jordan curve that has Hausdorff dimension bigger than 1. So it'll be, I mean, as a Jordan curve, it won't be that nice because it'll have Hausdorff dimension bigger than 1. But I mean, compared to what could happen, like it being a space-filling curve or something, it is nice. It's just topologically a circle and kind of divides the sphere of infinity into 2 connecting components, right? And so we have this like action of pi1 of the surface on the universal cover, okay, and it extends to an action on the boundary at infinity of three-dimensional hyperbolic space, which is just S2. We think of S2 in the Poincare ball model, and so right, and so kind of what we have is if we look at the 2 complementary regions that are homeomorphic to open disks, right? So the Jordan curve is going to divide S2 into 2 connected components. Each of these are homeomorphic to disks. And so we get, by looking at the action of pi1 of the quasi-Fuchsian manifold on the universal cover and how it extends the boundary at infinity, is we get this action of pi1, we get this action of pi1 of sigma g on the boundary at infinity on these 2 open disk complementary regions, where it's acting on these kind of like regions that are outside of the limit set. Pi1 of the surface is acting properly discontinuously, and we actually like mod out on both these sides and get mod out by the action of pi1 of the surface of G and G, and get a hyperbolic structure, right? So the upshot of what I just said is that for each of the two ends of our quasi-Fuchsian manifold, they're kind of limiting to these conformal structures that we kind of see in the universal cover by looking at the action of pi1 of the surface on the boundary at infinity. Okay, and right, and so to each quasi-Fuchsian manifold, we can look at the 2 ends and the 2 conformal structures that we get through this process of just like looking at the action of pi1 of the surface on these like 2 complementary open disk regions. And we can get 2 points in Teichmuller space that are just like the conformal structures of the quotients of when you mod out by pi1 of the surface under this action on these 2 complementary open disk regions. And so it's kind of theorem from by Alfors and Bears from a long time ago that these 2 conformal structures at infinity, like the conformal structures on kind of the 2 ends, as I just defined them, actually determine the whole quasi-Fuchsian structure. And conversely, if we have, any 2 points in Teichmuller space, we can find some quasi-Fuchsian manifold that kind of has those 2 conformal structures as its ends, right? And so this is like a really, really nice fact. And I'll just mention as an aside, it sort of there are all these different ways of measuring distances on Teichmuller space, and this kind of gives like a kind of another way of thinking about that, where you can look at you have 2 points in Teichmuller space, and then you just take the QuasiFuchsian manifold with those 2 points in Teichmuller space for its ends, and then one way of talking about like how far away those points are from each other in Teichmuller space is just to like talk about like how complicated the QuasiFuchsian manifold you get is, and so that's kind of a side thing that isn't that related to this talk, but it's kind of neat. But yeah, cool. So this gives us like really nice global way of parameterizing QuasiFuchsian space. That's pretty much the best thing you could even like think to ask for. But I mean, one question is, I mean, since kind of we look at the actual Quasi-Fuchsian manifold, all the actions kind of happening in the convex core. So I mean, one thing you could ask is like, is there a way to kind of parameterize Quasi-Fuchsian space from the interior, from kind of the geometry in the middle where it's kind of more complicated. Yeah, and so right, there's a way to do this in sort of a neighborhood of the Fuchsian locus, which I mean these Fuchsian manifolds, which are kind of like the model ones, and then we think of like right, if we take quasi-Fuchsian manifolds that are close to the Fuchsian locus, we'll just get like these boundaries at infinity that are like these Jordan curves that are like pretty close to the just like the round circle limit set for a Fuchsian manifold. So if we just kind of just deform a little bit off the Fuchsian locus, then it turns out we can answer this question using minimal surfaces. Okay, so right, so the kind of general like the ansatz for like how we want to parameterize quasi-Fuchsian space from the interior is we want to find canonical surfaces in the interior that say satisfy a differential equation, and then somehow recover the whole geometry of whatever quasi-Fuchsian manifold we're looking at from these nice surfaces that we have in the interior that are kind of canonical in some way. Yeah, and so what we're going to look at for this are minimal surfaces, right? So minimal surfaces are critical points of the area functional. So for this talk, we're just going to think of them as surfaces that have smaller area than any other surface in their homotopy class, right? So what kind of is going on here is if we just look at if we look at just surfaces that are just homotopic to the sigma g factor of sigma g times r, right? So just homotopic to sigma g times a point. And if we try to minimize area over all that whole homotopy class, then we know kind of the naive thing you kind of want to do is just take a minimizing sequence and pass to a limit and somehow get like a surface with smallest area or out of that after as a limit after just passing to a limit. And it turns out you can kind of do that. You can do that. I guess it takes a lot of work to make that argument precise, but there's by now kind of a pretty well-developed existence theory for minimal surfaces that lets you, at least if you're in 3 dimensions and looking at 2-dimensional surfaces, let you just if you have some homotopy class and then you're mining 3-manifold, just the work by Shane and Yao and Sachs back from the 80s lets you just find a minimal surface. And what we really need here is, I mean, we have like these ends that are flaring out. And so we know that kind of if like a surface is like going too deep in the ends, it'll have large areas. So we know that kind of minimizing sequences will have to stay away from the ends. And so we're in this compact region, we're able to pass to a limit. And so that's kind of what's going on there. So the point is we can kind of find these minimal surfaces in the convex core. And an analogy to think about here, if you haven't really thought about minimal surfaces that much, is if in any Riemannian manifold, if you have like a element of the fundamental group, just a homotopy class of loop, then you can minimize length and get a geodesic, right? If you're a negative curvature, at least you get a unique one. And this is kind of the analogous thing for if you have higher dimensional essential surfaces, you can kind of minimize area in that homotopy class and get a minimal surface. So that's probably a good analogy to think about if you haven't seen minimal surfaces that much before. Cool. So to say more about how this works with parameterizing minimal surfaces, parameterizing Quasi-Fuchsian space by minimal surfaces, or some part of Quasi-Fuchsian space by minimal surfaces, is, yeah, so it's basically this paper by Uhlenbeck. And the setup for the main theorem is kind of as follows. So you have some minimal surface sigma inside some hyperbolic manifold with topological types, just surface times r. And all you know about it is that its maximal principal curvatures are maximum of its principal curvatures is less than 1. Okay. And right. And so why 1? So 1, like the curvature of the hyperbolic metric is -1. So this is kind of saying the principal curvatures are smaller than the ambient curvatures, which are 1 in absolute value, right? The sectional curvatures of the hyperbolic metric are just -1. And then the principal curvatures are kind of, I guess, a way of measuring like how much the surface is bending relative to the ambient geometry. So for example, if you're totally geodesic, then the principal curvatures are just going to vanish identically. Okay. But in general, they're kind of telling you the difference between the curvature of your surface and its induced metric and the ambient curvature. So that's basically what principal curvatures are telling you. And so if they're kind of small relative to the ambient curvatures, that's kind of the hypothesis for just this Uhlenbeck theorem. Then the first thing you know is that M, it actually has to be Quasi-Fuchsian. It's not like doubly degenerate or something. It has to be kind of have this nice structure. And moreover, you can recover the hyperbolic structure on M just by looking at the conformal structure on the minimal surface and its induced metric, right? So the uniformization theorem says that like any metric you put in a closed surface, there's always some hyperbolic metric that is in the same conformal class. And so you get just a point in techular space. And then you get this holomorphic quadratic differential that is basically encoding what the principal curvatures are at each point. And sort of the fact that you're minimal and in constant curvature means that, you have the second fundamental form, and it ends up satisfying more equations than it otherwise would. And so you get this, really nice kind of description of the whole geometry just from the surface and the conformal structure on the surface, and this information about how it's sitting inside the ambient space, or really infinitesimal information about how it's sitting inside the ambient space. That's just this holomorphic quadratic differential. And so you're actually able to recover the whole geometry just knowing, these two pieces of information. I don't really can't really say too much about how this is proved, but what kind of roughly what happens is you're able to just, kind of have your minimal surface in the middle, and then you flow out normally, but just by the normal exponential map for the minimal surface. And you're able to show that that doesn't have any singularities, and you're able to kind of show that the metrics for the surfaces in the kind of the come from flowing out normally, satisfying ODE. And what Uhlenbeck does is she just writes down a solution to the ODE just in terms of the conformal structure and the holomorphic quadratic differential that you have here, and is able to just kind of explicitly write down the metric. And so, it's not that often in geometric analysis where you're able to like actually just prove theorems by explicitly writing things down, but this is kind of how this paper goes. So it's kind of cool. And then on the other hand, you can kind of reverse engineer this whole process where like if you have a conformal structure and a holomorphic quadratic differential, and also the conformal factor, and if it satisfies this PD, then you're able to sort of produce a Quasi-Fuchsian manifold just from this 1 and 2 here, right? So you're able to kind of so you get this kind of complete parameterization of this neighborhood of the Fuchsian locus, where you have this minimal surface with small principal curvatures. Right. So we call these Quasi-Fuchsian M that contain a minimal surface with maximum principal curvatures lambda naught less than 1. We call such M almost Fuchsian. Okay. And so kind of what the picture is here to just kind of draw a picture for the proof I just sketched of your theorem is, you have some unique minimal surface in the middle with principal curvatures smaller than the ambient curvatures. And what you're able to do is you just flow out normally, and you get these like mean convex foliations and you're basically able to recover the whole geometry, the quasi-Fuchsian manifold, just by looking at this minimal surface in the middle. Yeah, and so that's kind of what happens there. Right. So okay. So the transition a little. So there are a lot of different ways of measuring how complicated a quasi-Fuchsian manifold is, and it's been pretty well studied at this point by kind of Thurston School of mathematicians. I mean, so one thing you can look at is, I mean, you have this kind of canonical minimal convex region inside inside your quasi-Fuchsian manifold, and so you can just look at how big it is, right? So for a Fuchsian manifold, it will have 0 volume, but in general, it will have positive volume. And so kind of how big this convex core region is, where kind of all the action is happening, is one way of measuring how complicated a quasi-Fuchsian manifold is. Another way is you could look at the Hausdorff dimension of the limit set, right? So it's this, we get this like Jordan curve in S2 from any quasi-Fuchsian manifold. That's yeah, and that has Hausdorff dimension bigger than 1 in general, and so sort of as quasi-Fuchsian manifolds are degenerating, the Hausdorff dimension is going to maybe be approaching 2, like you're going to be kind of approaching a space-filling curve, and so kind of how far away you are from being a space-filling curve, that's like measured by your Hausdorff dimension, is one way of talking about how complicated you are. And another measure of complexity that's probably not as well studied as like 1 and 2 is just how complicated the minimal surfaces inside M are, right? So you can just look at canonical surfaces inside your quasi-Fuchsian manifold, and you can yeah, look at like kind of how much they're bending as measured by the principal curvatures, right? So if the ambient geometry is complicated, then you would imagine that kind of the canonical surfaces that you have inside your manifold have to also be more complicated to kind of accommodate the complicated ambient geometry. And so that's kind of a more geometric analysis way of measuring complexity. Yeah, and so I'd say these like coarser measures of complexity, like 1 and 2, and there are also a bunch of other ones I'm not saying have been like pretty well studied, but just kind of relating the principal curvatures to yeah, these other measures of complexity, I guess. In almost Fuchsian space, there's kind of a good picture that you have, but in general, as you kind of try to go beyond almost Fuchsian space and look at the rest of quasi-Fuchsian space, where you maybe have minimal surfaces that don't have maximum principal curvatures less than or equal to 1, then it's harder to say things. So that's kind of what the rest of this talk is going to be about. Is it's going to be about trying to kind of go beyond almost Fuchsian space and study the rest of quasi-Fuchsian space using minimal surfaces to the extent that that's possible. And so we me and Zeno kind of make some modest progress in that direction, but there's still a lot of things to do. All right, so yeah, that'll conclude the first part of my talk.